Sound is a mechanical wave. As such, it needs a medium to travel through. Let's take a look at this clip. In this clip, we will see an experiment that demonstrates just that concept. How does the loudness of a sound relate to its amplitude? Well, there is a direct relationship, meaning that the louder a sound, then the bigger the amplitude, and the softer a sound, then the smaller the amplitude. How does the frequency relate to the pitch of a sound? Well, it's the same relationship, a direct relationship, meaning that if there is higher frequency, then there is a higher pitch. And if there is a lower frequency, then there is a lower pitch. There is only a certain range of frequencies that humans can hear. Normally, a human can hear from 20 Hz up to 20,000 Hz. Or in other words, 20 Hz up to 20 kilohertz. Now, let's take a look at this clip that tells you a little bit more about human hearing and frequency.
How many of the following sounds can you hear? How old are your ears? Okay, if you can hear 8,000 Hz, you're both alive and not hearing impaired. But let's keep raising the frequency. Unlike other organs such as the liver or skin, the inner ear does not have the capacity to regenerate. In your ear, there are thousands of tiny nerve cells called hair cells. These are responsible for picking up different frequencies and sending the signal to the brain where it's processed. But as you age, the continual exposure to noise and loud sounds can break, bend, and destroy these cells. So why do the high frequencies go first? It turns out that the hairs tuned to high pitches are the first to encounter sound waves. As a result, they experience more stress and tend to degenerate earlier. Which is why the older you are, the harder it is to hear high pitches.
The speed of sound in air is approximately 330 meters per second. In liquid, it travels about 4 to 5 times faster, and in solids, it travels about 15 times faster. Can you think why this is the case? Pause for a moment and let's see what you can come up with. Let's remember that a reflected sound wave is called an echo. Echoes and sound waves can be very useful in the fields of medical industry and fishing industry. Now, let's take a look at an example or two where we calculate distances based on the echoes of sound waves. Okay, in this example, a fishing boat sends out an ultrasonic impulse to some fish below. It takes 0.80 seconds to receive the echo. How deep are the fish if sound travels at a rate of 1500 meters per second in water? So to work on a problem like this, as always, it is customary to start with a diagram. So we have our boat, it sends some ultrasonic waves that bounce off the fish and are then received as an echo back at the boat. We identify our givens. The time is 0.80 seconds. The speed is 1500 meters per second, and the distance is what we're looking for. So we have our equation triangle. Speed is equal to distance over time. Using our equation triangle, distance is then speed multiplied by time. So we have 1500 meters per second times 0.80 seconds, and that gives us 1200 meters. But that is not our answer, because if we look at our diagram, that is the distance to the fish and back up to the boat. So to find the depth of the fish, we have to take that 1200 meters and divide it by 2, because it is only half the distance that the sound actually traveled. So that is 600 meters. Another way we could have done it was, we could have divided the time by 2, because it takes 0.40 seconds to reach to the fish and another 0.40 seconds to reach back to the boat. So if we had simply divided this by 2 first and then multiplied by 1500, we would get the same answer of 600 meters. So now let's look at another example. In a storm, a flash of lightning is seen and then the thunder is heard 3 seconds later. If light travels at a rate of 333 meters per second in air, how far away was the lightning strike? So here we have our little diagram. Here's you, the person who has seen the lightning strike and then 3 seconds later heard the thunder crash. How do we determine how far that lightning strike was from you, the person? So we identify our givens. The time to hear the thunder is 3 seconds. The speed of sound in air is 333 meters per second. What is the distance? So we know that distance is speed multiplied by time. So we take the 333 meters per second and we multiply that times 3 seconds. Just like before, the seconds cancel out and we're left with 999 meters, which is approximately 1 kilometer. Unlike our previous example, we should not take that 1 kilometer and divide it by 2. Why? Well, the sound does not travel from the person to the lightning and then back to the person. It doesn't travel both ways. It's a one-way trip. So we should not take that 1 kilometer and divide it by 2. It is not an echo, in other words.
Hey, don't try to take this away from me. This is the only thing I've ever been good at. Well, this and timing my farts to a thunderstorm.
Why don't we all go ahead and turn to page 6 in the handout. The first thing you're going to notice is a bar graph. And what that is to indicate our international sales, which peaked, of course, during the last quarter. But now we're expecting that to drop off as we enter the colder weather.
The storm's moving away.
That was a very funny clip, wasn't it? But let's take a look at the science of it. The question I want to ask you is, how is it that Peter Griffin knows the storm is moving away? Pause for a moment and think about it.